Okay, it's time to start. Hello, everyone. Um, so you've seen in the chat that this is third lecture. Next lecture is third. There's a second lecture next to the third one, so it's deadline for homework. Yeah. The goal of this lecture. So last lecture we defined the classes P, X, P space, X space. And the main goal is to prove that P is not equal to X. And so the proof is very similar as undecidability of the halting problem. But first, we will talk a bit more about Turing machines, repeat a few things. So, so we define Turing machine as some tuple. But for now on in the next lectures, we will use Turing machines as deciders, not as mappings from string to string. So that was just for first learning about Turing machines. We use it as input-output machines. We will do this again when we speak about reductions. But for now, we use it as deciders, and then we will define it. So it's defined by a set of states that can be occupied by a control head. There is a tape alphabet. What else do we have? We have a transition function, a start state, and an alphabet for the inputs, which is denoted by signal. So remember, alphabet means non-empty finite set. And then we use the star notation. So all the inputs are from sigma star. That means finite space of symbol. So most important, almost very often, we use as input alphabet binary strings. So programs are viewed as binary strings. This is the empty string. Okay, everyone knows already, just make sure that we understand. And the goal is to decide a language. Previous lecture, we explained that if we can solve decision problems, then for the then we can also solve production problems with maximum polynomial overhead. We gave a few examples, and soon we will understand that for the class NP, we can always make such transformations. Well, and all in this, like a huge number of industrial optimization problems, they're most naturally modeled by a problem in NP. So that's why we only care about deciding a language. And so when a Turing machine is a decider, we will add two states, which are called accept and reject state. And so if we start the machine on a certain input, whenever the transition function is undefined, so transition function is a function. So remember, at each moment, computation had to read the tape cell, write something in the tape cell, and makes a move. And and these three things depend on the state that reads and the control state that has. So the state of the computation head. So it is so delta is a function of q times gamma 2 gamma times, and then we have left or right, and then times q. So this is transition function. So this is a partial function. So it might happen that on some state and some symbol machine that has no rule what to do next, and then machine terminates.
Excuse me.
And so
camera to the right a bit. So,
I put you a bit loud. Yeah, you are already loud.
can you move camera to the right so we can see the right side of the desk?
Yeah. I will. Okay. Yes. So I'm just repeating from previous lecture now, so it's a little bit boring, but for some people, okay. So it's a partial function when delta is undefined because it's in a state and scans a certain symbol. Then the machine halts. If machine halts in an accept state, then we say that the machine accepts the input word. And similar for reject state. That's how we use the machine as this. I mean, there are many ways how you can implement a machine to be a decider. Like you can say, let's write output 0 or 1. That all doesn't matter. So this definition of Okay, so so now we view a machine as a device to say accept or reject, and so we can define the language recognized by the machine. That's just all the strings that are accepted by the machine. So we say that a machine recognizes a language if it accepts precisely those strings in the language. So note, a language is a subset of sigma star. So the language recognized by machine are recognized by machine those strings that are end in an accept state. And here, when we speak about recognition, we don't care about inputs that are not in the that are not in the language. So we say it recognizes the language. The only requirement is that those strings not in the language are not accepted, but it may happen that the machine gets in a loop. So halting problem is an example of recognizable problem. Like the input is a program, and the question is, will the machine terminate on this input? Or some other. Okay, so input is a pair program and machine. Does the machine terminate? So does this other machine terminate when you're given this program? Okay, so it's recognizable, but there is also deciding a language. When do we say that the machine decides a language? Then for every input in sigma star, the machine should terminate either an accept or reject state. If it's not in the language, of course, reject, otherwise accept. So that's the definition of deciding a language. Okay. So that's for one-tape machines. We can also think about multi-tape machines. And multi-tape machines are equally fast if we don't care about polynomial speedups or polynomial scaling of the runtime. So in our course, remember, we care about which problems are solvable in polynomial time and ones in the exponential times. And in the last lecture, we will speak about parameterized complexity, where we try to implement brute force searches and optimize the coefficient and the exponent. So for us, polynomial slowdowns don't matter. And so we can either use one-tape Turing machine or multi-tape Turing machines interchangeably. And this is guaranteed by this theorem. And it just say that whenever we have, oh, sorry, I need to first say what is multi-tape Turing machine and how it works. But I already quickly said last time. So everything is the same as before. So it's again defined by this 7 tuple. But now delta takes k symbol takes as output, and so it will read from k tapes, and then it will write k different symbols on all of the on all the computation heads. So it has, for every tape, it has a computation head. If there are k tapes, there are 7 of them, and then it can write. So it reads everything, and then depending on everything that's read, it can write everything and make individual moves, and then go to the next thing. So this is read, write, move operation. This is the elementary step. Okay, and so now there is finally the theorem. So if we have a Turing multi-tape Turing machine, can be simulated on one-tape Turing machine with quadratic delay in the time. Okay, so we have to if the first machine runs in at least a linear time, then the time is quadratic. Okay, and how it's proven? So maybe don't know if people already know this. So here you see a Turing machine, and we need to simulate it using one-tape Turing machine. And so we will do some very natural thing. So we need to represent many tapes on the one tape, and we just do it after each other, the natural thing. And so our machine will have the same alphabet, but we also allow to mark certain symbols. So what does it mean to mark a symbol? We take just, our machine will have 2 copies of the same alphabet, plus some separation symbol. and we will place marks on the position of the computation heads, and then the simulation goes quite easily. So here I draw a one-tape Turing machine. And so we place a special mark symbol between the two tapes, and then we copy the symbol. So here we have 110. Then we have a special symbol to start the second tape. Okay. So here, this machine, so when we simulate this machine, we will have a state Q. Here are the marked symbols, and on the position of the computation head, we use a marked copy of the symbol. Okay, I need a bit more space. Sorry, I'm the states. Okay, the states are a bit hard to explain, but I'm just saying that here we have this union, the marked symbol union this. Then we have some delta prime, Q prime. Okay, let me just write the tape alphabet. Will be this thing. And so we just use marks to identify the beginning and the end of the tapes. And so now you can guess how we simulate one computation step. So we will always start above the first symbol. Then the machine will scan over this and remember the marked symbols in its computation head. And remember last time we can keep finite information in the computation head because we can use any finite number of states. So when we write everything, then we return and make the updates because the machine knows. So basically here we will have, then the states here will be gamma to the power k times, and then we need 2 passes or something. So then minus some finite set here. That will be roughly the states. So here are the states to remember the symbols that are red. Okay, so this is a bit a rough idea. So this is how you can prove this. So it's a bit high level overview of the proof, but I think it's quite clear. And so that this simulation just imitates the multi-tape Turing machine. So we just need to check how fast this machine is. And so how do we get the quadratic time?
What is W?
Because between each
Input word. Yes.
because you have to move head between each operation in every
Yeah.
virtual head.
Yeah. So we keep the tapes, and so so each time the computation head has to move over all the steps. Oh, and I forgot to say something important in the simulation. What happens if, for example, the last tape head moves to the right here, or the one but last head in the middle tape, the head moves to the right. So here we will update the copied symbol. It needs to move to the right, but we don't have any space. So then we break the simulation and we move this part 1 cell to the right and insert a blank here. So in right moves, we need to be careful. And so at any moment, the length of the tape in our simulation that we remember will be the rightmost position where the computation head of the tape has been. So this is just a small interruption. And then, so to simulate one step, the runtime, like already was said, the runtime that is needed is just the total length of all the tapes plus some constant. So it's proportional to the total length of all the tapes, because we just have to go back and forth. basically 2 times plus maybe we have to go again back and forth when we need to move everything to the right. So simulating one step is proportional to the space. But what is the maximal space that we can get after simulating t steps? So in the beginning, the space that we have the input string, and then the other tapes are just at 2 lengths, at 2 cells to the simulated length. So initially, and at the first step, to simulate the first step, we need the first computation step. But while we continue, the our tape that represents the other tapes, so the relevant piece becomes longer and longer. And the maximal length it can have after t steps is order of t. And so k times t plus some constant. Why? Because in the worst case, we go to the right on all the tape in every step. So after t steps, all the computation heads are in position t plus 1. So then here the total representation is k times t plus 1 plus the space of the hashtags.
In what case we do need to go to the right side of the tape?
Yeah, for example, here is the middle tape. So initially the computation head is in the beginning.
Mhm.
If this head moves to the right, then we want to update corresponding symbol here. What does it mean? We want to have another blank here and move the dot here. So imagine it writes the same, again, a blank, and so it doesn't change anything and just moves to the right. Then we need to insert an additional symbol, sorry, not here, but here. Right?
Do we need to
Okay,
both
so-
tape?
Yeah, so if after the first computation step, the computation head is here, then we need in the middle tape, we need to have two symbols because we are using now the first part of length 2. So this single tape needs to remember all of the tapes that we have used so far. And maybe in the first step, okay, it writes 0 and moves right, the middle tape. So then we want to, after we simulate the first step, we need here, we want here to have a 0 followed by a blank. So we want to write here a blank with a dot. But now you see I'm forced to delete a hashtag. It will break our structure. So what we need to do then is interrupt the computation and move everything 1 cell here so that I can place the hashtag back. And so this escapes our simulation. Okay, I'm explaining badly, but it's also not too hard. So should okay, I tried to read the faces. It seemed to be good, but some faces are without any expression, and
This bound precise, I mean, is it the best bound we can? Can it be proved that we can simulate multi-tape Turing machine with
subquadratic, it's
with
impossible.
less
Yeah, and with no, it's not possible.
than
Because palindromes is counterexample. We know palindromes on one tape Turing machine needs at least quadratic. So this can be proven using crossing. Okay, it's not important. But we have on one tape, it can be done in linear time.
I think you can get rid of that plus length of W.
If you're careful, you might
for
be.
normal algorithms, f of length of W is at least length of W because like algorithms should read all the input. Otherwise, it's
Yeah.
probably useless.
Well, if you speak about the language that accepts the first bit according to the first bit or something, yeah, and then I want to have a theorem. I don't want to say that, okay, if the machine runs at least in linear time, so I just added the length in order to have simple statement.
There's no requirement for that, I think. I thought at first to replace the alphabet of the tape by k couples of symbols. Then you can find the
Yeah, it's another way.
without.
Yeah. Yeah, you can do it, but then you have to do it very carefully by choosing the right alphabet so that you don't need to rewrite the input.
Just renumber states, so the initial states
Yeah.
correspond to spaces in the non-first state.
Oh, okay. Somebody wants to record, but it's streamed on YouTube, so it's okay. Yes, so that's our theorem. And so there are some exercises. But this, so it doesn't, so in Sipser, the class time f of n, so if f is some time bound. So for example, f of n equals n squared quadratic time. In Sipser book, the class time of f is defined using one-tape Turing machines. So we say that the language L is in time f if there exists one-tape Turing machine that recognizes that decides L in time with order f of n steps. That decides L on input W in order f of length of W steps. Okay, so this is non-standard definition because in other books they use any multi-tape Turing machine. But okay, let's keep this book, and then similar for space. Note that for space is also defined with one tape Turing. If there are more tapes, then we just add up the rightmost positions of the computation head. Or we take the maximum, it's the same because there is big O notation here. Okay, and then we say that the class P is the union over all C of time n to the power C. Then P space is the same. Is equal to union over C of space n to the power C. There is X. Is equal to the union over all C, 2 to the power n to the power C, and X space, but we don't need this for now. So we have P equals P space, P is in P space, which is in X. So it's still readable. Can you read it?
No, we can't.
Oh, sorry, I should write here. P is in P space. Is in X. Okay, so the first inequality is clear, right? If machine can run in f of n time, it can it can visit at most f of n cells. The second one is a little bit harder, but after the seminar, you might have an idea how to prove it. So idea is to count configurations of Turing machine. So let's consider configurations on one tape Turing machine. So the whole description of Turing machine, if there is just one tape, what do we need to know? 3 things. The state of the computation head, the position of the computation head, and what is written on the tape. So this is an element of Q, this is an element of N, a natural number, and this is infinite sequence of tape symbols. Okay. So Now I claim that if a machine makes a computation using at most S tape cells, then it will use at most 2 to the power order of S time. Why?
Size gamma to the power of n.
Yeah. So, okay. So I claim if machine uses S cells, at most S cells, then terminates in time 2 to the power C to the power S, where C only depends on the machine and not on S. So why is it true? Well, the idea is that if a machine visits a configuration twice, that's what's configuration, the state of the head, the position, and what's on the tape cell. But if we consider a tape cell of a machine that visits at most S cells, we don't need to think about infinite string. We can think about finite string because the part after S is irrelevant. There are two configurations. If a configuration is visited twice, the machine is in an infinite loop, and so it doesn't terminate. But in the definition of time, we consider deciders. Should be a machine that decides, so always terminates. So this cannot happen. So the runtime is at most the number of configurations. And the number of configurations is, so number of configurations is size of Q times the position, which is between 1 and S. So S possibilities and size of gamma to the power S. Possible countants of the thing. And this is precisely 2 to the power CS, where C depends on the machine. So for large S, okay. Yeah, but okay. Yeah, so now we have proven that if we use polynomial space, we need at most exponential time. So P space is an X. Okay. So we understand now that there are two inclusions. And the goal of this lecture, we don't know, nobody knows whether P equals P space.
That's equal to NP.
Yeah, this is similar. And P is between P and P space. So here we have NP, but we don't know the definition yet. Okay. So
Similar, but they're not equivalent.
no. There's open problem whether they equal NP and P space. But okay, next lecture, this will be the topic for next lecture. Okay, so Hamiltonian path is a problem that nobody knows whether it's in P, but it's in P space. It's actually in NP. But why can we solve Hamiltonian? Okay, I always skip to something unexpected. Let's first look to what this means. So the goal of this lecture, so it's open question whether P equals P space. If a computation runs in small space, can we make it fast? Then there is a question, maybe a computation runs very long. It might be true that P space is equal to X. That means that if a computation runs very long, we can at least do it with small memory. It's unknown, open question. But we do know that at least, so we cannot have equality on both. It would be an amazing news if at least one of them was equal. But we cannot have both of them equal because we will prove that P differs from X in this lecture. So this is our goal. Okay.
Sorry,
Yes.
can you explain, please, what does it mean, P less or equal P space?
P less or equal P space means that every problem in P is also in P space. So P space is a set of languages. So that means inclusions as sets. So here, so P is a set of languages, and P space is a set of languages. So we say that a language belongs to time of F if there exists a Turing machine. So time of F is a set of languages.
Okay, I understand. Thanks.
Yeah, very good. This is fundamental. If you don't know this, then lecture is very difficult. Okay. Yes. Okay, and maybe it's time to speak about some problem that's in P space, but not known to be in P. And so it can be Hamiltonian cycle. So you remember you get a graph. It means n squared of bits in our input because we will represent graph by adjacency matrix. And so n squared bits representing the graph. And the claim is that it can be solved in polynomial space. So how does it work?
Just iterate through all possible
Yeah.
paths.
So brute forcing will work because we just need, we can represent, to represent the cycle, we just need a list of n nodes, and each node is a log n bits. And then we will just try all the possible strings of length n log n and check whether they represent a Hamiltonian cycle. And so like we increase a binary counter, so we just need to keep one counter. It will take exponentially long, but the memory we need is less than linear in the input length.
It is linear. No, it's sorry.
Well, it's a bit messy because the input is n squared if we have n nodes, and our list is n log n. So if we ignore the input itself, then the actual memory that we modify is sublinear. Of course, we cannot have linear memory use because we need to remember the input. So this, of course, valid remark, but okay. So yes, actually, to measure space, you can speak about sublinear space, but then people use a Turing machine with a special input tape. And it's not allowed, so the input is there, but it's not allowed to write on this tape. And then there is a second work tape, and people use how many cells are used on this tape. Yeah. So this is in lecture 8, we will use this model. At least about 8. We will see. It should be right. Okay. Yes. Okay. And so now we have explained our first goal. Let's now speak about a halting problem. So, but first, let us prove a very simple theorem. We will prove that there exist languages that are not decidable at all. No Turing machine can decide that. And this is kind of easy to prove. And the plan is to think about countable and uncountable sets. So let us repeat what is countable set. So a set is countable if you can put all its elements in a row. For example, natural numbers are countable. That's very easy. 1, 2, 3, 4, and so on. Every natural number will appear in the row.
Like by definition.
Yeah. So yeah, almost the correct mathematical definition. But okay, rational numbers or pairs of natural numbers, 5, 7, and so on. Let's make easier the integer numbers. So the negative and positive natural number. So there also, you can put them in a row, 0, 1, -1, 2, -2, and so on. Then pairs of natural numbers, you can also put them in a row. So you can have 1, 1. Let's be mathematicians. So what do you like? 0 is a natural number, yes or no? Or it's okay. Let's. I already started writing, so it's too late. 2, 1, and then you can have 3, 1, 2, 2. So pairs of natural numbers are also countable because we can create a list that contains all of them. So pairs of integer numbers are also countable, right? We can also put them in a list. It just we need the rational numbers, their ratios. We can also put them in a list because they're basically pairs of integer numbers. What else? Oh, bit strings. We can also put them in the list. So we have the empty string, the 0, 1, 0, 0, 0, 1, 1, 0, and so on. Right? So bit strings are also countable. Okay, and then there is a guy Cantor, and he came up with a set that's not countable. And the set is set of infinite bit sequences. So he says whenever somebody comes up with a list of infinite bit sequences, he provides one that is not in this list. So imagine that there is a list 0, 1, 1, 0, and so on, 1, 0, 1, 1, 1, 1, 1, 0, 0, and so on. And then his answer is, okay, how do I find an element that's not there? Let's look to the diagonal and invert it. So here we have the diagonal. So the negated diagonal is equal to 1, 1, 0, 1, and so on. He says this sequence cannot be in the list because if it's at some position in the list, is it equal to, so there is some place here. Sorry, if it appears here, then we will have, when we look at if it's on the ith position of the list, then we look to the ith bit and have a contradiction. So if we have this sequence 1, sequence 1, sequence 2, sequence 3, then he said, let us define di equal to not si.
SI.
Yeah, sorry. And D of I, okay. So now the idea of proving halting problem is very similar. So let us so what we will do is we will make okay, sorry. First, my promise, why does there exist a Turing language that is not decidable? So languages we can associate with infinite bit sequences. So how does it work? So we can associate empty string 0, 1. So we will associate the zeros and 1 with the corresponding string to be. So here let's make an enumeration of all the strings. We know the set is countable. And let us interpret the sequence as whether this string belongs to the first language, yes or no. So we can associate sequences with languages. Right? So you're with binary languages or even unary languages if you want. Okay, but then then we have the same result. So number of so the diagonal presented. So for every list we can come up with for every list of languages we can come up with a language that's not in the list. So languages are uncountable. But what do we know about number of Turing machines? Okay, number of Turing machines is a little bit tricky because they're defined by these 7 tuples and they are just finite sets. But when we can represent Turing machines by bit strings. Turing machines, their operation can be encoded by bit strings. How do we do it? So we can associate the sets with numbers in binary. And then the transition function maps numbers to numbers. Since we associate these sets, a pair of numbers to triple of numbers. But we take inputs from a finite set and values also from a finite set. So it's easy to encode a Turing machine in binary. Every Turing machine can be represented by binary code. But we know that the binary strings themselves are countable. So that means we can make a list of Turing machines that contain all the Turing machines by just interpreting all the bit strings as codes for Turing machines. So it's clear Turing set of the number of non-equivalent Turing machines is countable. So the set of decidable languages is countable. The set of all languages is uncountable, so there must be at least one language that is not decidable. So yeah, this is hopefully okay. Now let's prove that there is a specific language that is undecidable. It's the halting problem. So let's write down the definition. So it contains the halting problem is a set of pairs. So where there is a bit string that we interpret as a machine. Okay, let's use X for a machine and P for an argument. And so, okay, first we need so here is the halting problem. The input is a machine represented, for example, in binary, using a binary encoding, and a program for this machine, also represented in binary. And so remember that this machine has some input alphabet sigma. The sigma we can associate with numbers, and then the list of such numbers can represent a program P. So we can encode everything in binary. And so we can define the halting set of pairs of strings, for which the encoded machine on input P halts.
Can refer the pair of machine and its input as a single machine without input. So
Yeah, this is also so there are various variants of the halting problem. And they're reducible to each other in polynomial time and so on. Okay. So now we want to prove that this problem is undecidable. So how will we do it? We will construct. Let's consider a list of all the machines just by enumerating all the bit strings. So we can associate bits. So we can, okay, why not use the bit string? Epsilon, M0, M1, M00, and
what's that? What's a method?
empty string.
Ah.
Yeah, okay. I wanted to write a bit faster, but then it's not faster. So we can think about all this list and then create the diagonal element. And so let us say that X is in the diagonal language if and only if X is not in MX. So let us define D. So this definition of D. So here, let us have a definition of D.
MI is a language which is decidable by a machine, right?
No, this is just a definition. I didn't prove yet that D is decidable.
No, what does it mean that X is in
Yeah,
the
okay,
machine?
yeah. So this means
That's it's
MX,
decidable line of the machine, right?
yeah, MX accepts X. So X is in the language recognized by this machine. So I forgot to say the theorem that I want to prove. this halting problem. H is not decidable. So in other words, there is no Turing machine that decides the language H. So remember, I told you what is decides for a language. There's a machine that accepts precisely those inputs, that accepts all inputs in the language, reject all inputs not in the language.
If X is in G, if if X is not max.
Yeah, thank you.
No, that's definition of not diagonal.
Yeah, the negated diagonal. Okay, so let's write it here. Yeah, sorry. Definition, I will call the language D bar. So it's some funny names and okay, and this means that MX rejects X. Okay. So now our plan is, so we have the special language. Now let us prove the theorem. So by contradiction, we will prove it. So we will assume that H is decidable. Then I claim that this language X D bar is also decidable. So what can we do is we can check, we can give if it's decidable, then we have a program that given a pair M and V tells us whether it's in the language yes or no. So we will give our pair MX and with input X to this algorithm. And we know whether MX on X will help. And so if it helps, we can know whether it's rejected or accepted. And so we can do the opposite. So we can have our program for the bar, but just negate the answer. Okay. So our assumption implies that the bar is decidable. So we've constructed a machine that decides D. So our machine must have a binary description. So let this description be Y. Y, and so MY decides D bar. Oh, assume
So it's D.
D bar, sorry, yeah. And so assume H is decidable. The first step. Then second step, MY decides D bar. We constructed the decider, and now we have a contradiction. So doing that is Y accepted by MY is the question. Well, what does it mean? We know that MY is the same as D bar. Sorry, so yeah, it is D bar. And then by definition, so by our assumption, MY this, so this is the same. But by definition, D bar does precisely this. Why? It accepts precisely if it's rejected by MY. Is it visible? Okay, almost. So that's what we write here for the camera. Y not in MY. So now we have a contradiction. Y in MY if and only if Y not in MY. So it's contradiction. So our assumption must be wrong and H must be undecidable. Okay, so now people think, so some people have trouble focusing. It's because you already know or you don't understand.
I'm going to know.
Okay, yeah. Okay, some are smiling, so that's good. People already know them.
But I do another proof, like if we have an algorithm, we construct a new algorithm which loops. But I don't remember that proof. It's completely another one, but I think it's related.
Yeah. So like if you try to implement such thing, then you try to follow the definition and you get into infinite recursion, and that somehow, if you think more about what's happening in the proof, that's what's happening. Okay, and now we will do the same reasoning again to prove that P is not equal to X. And then our lecture is finished. So, and it will be early, I think, because we have half an hour left. Okay, so our language will be slightly different now. So, okay, we want to prove that P is different from X. The language that is in, so we need to find the language in X and prove that it's not in P. So here we will have a variant of this language, but we need to make sure it is in X. So that means we need a decision procedure, but this is an undecidable problem, checking whether X is not in MX. We've just proven that it's undecidable. Or proof of undecidability of halting problem starts from saying that we get contradiction if we can decide this. So we need to find an easier language so that we can prove it is an X.
Halting problem from binary to
Yeah. So we will say that finite, that's too easy, because we still need to be different from every problem in P. So your idea will give you a language that's in P, that's also not good. So a language that's hard enough so that's outside P, but still in X, that's what we need. And so the plan is to say that X is not in MX, or and let's say that MX. So the similar.
Max is in MX.
So let us say that. Now let us say that MX accept X in 2 to the power length of X time. And then we get something that we can check in exponential time. And so we say that X is an inverse diagonal if X accepts, sorry, if I'm getting to see now very fast. If X rejects, sorry, not X, but MX rejects X in time. Okay, I will say simulated time. There are some subtleties. Time 2 to the power length of X. Okay, so here is our definition of D bar. So we will put X in D bar if MX rejects X, and we will, to check whether MX rejects X, we will run a simulation of MX by a universal Turing machine. That's a Turing machine that can simulate all the Turing machines. Actually, I forgot to tell what is universal Turing machine. I will do it after the lecture, but it's very easy to believe that you can make a program that gets 2 inputs, a description of machine and a program, and then simulate this machine on the program. That's when you have a C++ piler for Python. It's basically the same thing. So this is easy to believe. So we will fix such a simulating machine. And when we get X, we will look at machine MX and simulate it on X. But we run the simulation for 2 to the power length of X steps.
Do we need this universal Turing machine to have at most polynomial overhead?
Yes. And so the simulation might go a little bit slower.
Actually, mine is
Simulating.
not that slow, it's just because it's only low.
Yeah, we need a certain exponential overhead. It's enough, so it's very easy to believe it's possible. But actually, you can do this with constant factor overhead when you're using one-tape Turing machines. So you just carry the description of the other Turing machine with you. Okay,
Why
but
isn't
I
that
will
quadratic?
speak about the details later. I forgot an important step. But it's just easy to believe that if you have one machine, well, if you have a one-tape machine that can remember the instructions of a machine that it wants to simulate, take the instructions with it and just copy, do what. So the description of other machine is like lookup table. And then the universal machine will simulate the original machine, but to know what it will do, it will look in the description of this machine it simulates to know which symbol the certain cell needs to be replaced.
Do you need amortization to remove the description?
No, so the other machine has constant length. Okay. When the length of the machine is not constant, then well, the length of the other might so
I think it's easily to emulate on a two-tape machine, like with one tape with the program and another tape with the
yeah,
memory.
that's even better. Yeah. Okay. Yeah,
And
thank
then,
you.
but then we have
Quadratic overhead, but the square of exponent is still exponent. Okay, but let me first tell the proof. There are two different speeds now. So let's first see. Actually, okay, let's do it in the no, okay. So let's not worry about overhead of simulation time at the moment. So the problem is that simulation is a little bit slower, and I will convince you later that it's not a problem. Actually, these people, clever people, already told why it's not a problem. Okay. So
You still haven't said why we can't just use normal time here.
why we cannot use why we cannot use normal time. With normal time it also works, but we want to do the same thing for space, and for a precise version of the theorem later, and therefore I switch to simulated time. Oh yeah, okay, sorry, it's okay, let's indeed present the simplest version. Let's not try to do the general version right away. Let's then do the power length x. Okay, forget about simulation. Thank you. Yeah, it's not good. I should prepare better. But instead of writing notes from previous lecture, I should have prepared this lecture. Well, but I thought I remembered everything, but it's every year I mess up this lecture. Okay.
In the same way?
No, I always have a different plan. So if you watch the movie, then but this is already much better because usually I go overtime for this lecture, and now we will be shorter if everything goes well. Okay.
Because we forgot universal Turing machines, right?
Yeah, but now the proof is really easy, and then I just have to say what is universal Turing machine, and we're finished. So if things go smoothly, thanks to your nice advices, we will be finished earlier, despite my poor preparation. Okay, now let's go back to the proof, and we will see that almost nothing changes from the previous proof of undecidability of halting problem. So, okay, we need to now understand two things about d bar. We need to know that it is an exp, and we need to prove that it's not in P. And then we have proven P not equal to X, because of d bar. So first, let us think what you already proposed. Why is d bar in EXP?
Because there is a universal machine.
Yeah.
Simulate M with polynomial overhead, and then we run.
Yeah.
Just simulate it, like we count steps.
Yeah. So this is because what we've been discussing. There is a machine that takes description of other machine and a program, and then simulates 2 to the power x steps. So this many steps, and it will have quadratic overhead. The runtime will be, so it will simulate t steps and time t squared. And so the simulating, yeah, for one tape machine, it will be a one tape, so it will be a 2 tape machine that will run for order t steps, and then when we transform it to 1 tape machine, it will, okay, but that was not the plan, so it will run for order t of square steps to do the simulation, and so it will be equal to order 2 to the length 2 of x steps. So that will be the runtime on input x. So that means that places this in x, clearly in x, because we can have any polynomial of x in the exponent. So so d bar is in x. And now the question, d bar not in P. So let us consider now a machine. Yeah. D bar not in P. Okay, so let us now take any polynomial time Turing machine my. That's all. For every Turing machine, we can get its binary description. Okay, and so let's try to follow this thing. So so let us assume my decides d bar. Then we have y and my if and only if y not in d bar. And so it will do the opposite, assuming that the polynomial of y. So let us take the machine. So let us say that my is body time runs in time p. P is some polynomial. So m of w runs in time p of length of w. Okay. So we know that if p of length of y is smaller than 2 to the power length of y, then the answer of m of y will be the opposite. And so so y in my if and only if y not in d prime. So under this assumption, we will have that d is the negation of what my is doing on itself. And under this assumption, we will have that this equivalence is valid. Sorry, this equivalence is valid here. This is by assumption that my simulates d bar. So in this case, we are good. If their polynomial is small enough so that the value in y in the length of y is smaller than 2 to the power length of y. Okay, but now we still have a problem. What if this is a huge polynomial? And so y is a fixed string, so we cannot guarantee that this is always true. So then let us look to another machine, a machine that operates precisely like y, but in its binary description, we insert all types of junk states. State of the computation head that can never be reached. So let us call this the description y plus k. So here we have added k junk states with plus k in the subscript. We know that machine M y plus k operates precisely as machine M plus y. Okay, now we will mess a little bit with our inequalities. Let's replace everywhere y by y plus k. And then we are good. So now it works. If we choose some k long enough, we will have that my plus k will be a very long string, and this must be true. And this finishes the proof. So this is kind of artificial hack, but it works. We just artificially make the description of the machine longer. And then we basically have the same machine. So if my decides d, then also my plus k should decide d. And then we obtain contradiction.
It's creation, like when you have a program and we create another program which is like behaves just like initial program, but it's like harder to understand.
Yeah.
How would you call it?
Obfuscation.
Yeah.
It's in cryptography, something that I'm supposed to learn. So, but okay, later.
We will have that.
Huh?
Will we have that at some point?
In maybe in the cryptography course, but not in this course. But I think there are very few algorithms known for program obfuscation. So this cryptography where you have a program and you want to send it over public channel, and the opponent should have somehow no clue what this program is doing. But I will not speak about it because
Well, that's exactly what we do.
yeah. Well, it's not so hard to obfuscate. Like you can get rid of unreachable states in polynomial time. Okay. Yes. So now I just have to explain why we can simulate, why there is a machine that receives another machine and simulates it with quadratic overhead. So let us say this more precisely. But wait, let's ask one more time. So do you want me to repeat this proof? Because that's what we're doing now.
Please do it.
Yeah. We still have 10 minutes. And just saying what is universal Turing machine is not so bad. Okay, so it's clear for everyone.
No.
No?
No.
Okay. So you do not agree with this thing?
Yes, I don't get how you prove this.
Okay, yeah. So let's so first step. Okay, so I will directly say the full proof. So let's consider a machine my that runs in polynomial time. Okay, then we will transform this machine, its description, we will add junk states and make the description artificially very long so that the runtime is smaller than 2 to the power length of its description. Okay. So the machine operates in the same
But
way.
it's still self-rejecting machine and all of that will.
Yeah. So D is the self-rejecting language. So this holds this equivalence is now by definition of D and this assumption. And so the machine terminates in less than this many steps. So it is in this language if it's not if it rejects itself and vice versa. So this is automatically, and this is just our assumption to obtain contradiction. So we have obtained contradiction. So basically we have proven that our machine MY makes a mistake in precisely this element. So we could transform this proof to a direct proof. Give me a machine, and here is the string on which it make a mistake for this language. So polynomial for every polynomial time Turing. So we've proven that every polynomial time Turing machine will fail to recognize this language. D bar. Okay. So now let's say what is
Is there any known example for language that is in P but not in X? Oh, no. We just presented one.
yeah. But the question is there a natural example? And well, any complete language is natural example. And so there is some funny game with the drawers. So there is a drawer with holes drilled in it. So how do you call this cupboard where you can move drawers back and forth? Okay, you understand, right? Just where you put books or folders or something like often below the desk, but it doesn't have a top, and in the drawers there are holes, and there are two players. So in turn, one player can move precisely one drawer, and the first player wins if he can move the drawer in such a way that you can see the floor. So the bottom is free, and just the drawers have holes. In some, so there is some natural number for grid, and then there are a bunch of holes. And then there's a question: does the first player have a way to see the floor? And so this is most natural example of X-complete problem I'm aware of. So, okay, for the other students, so they ask for natural problem, and I say X-complete. So in every computational class, there is a set of problems that are among the hardest of this class. If you can solve one such problem, you can solve all the problems in this class. So here we presented an artificial problem in X that's not in P. But then to find a natural problem, so if we find one problem now that is not in the smaller class, then we know that all the problems that are among the hardest inside this class, so the complete ones in this class, are also outside P. And so that's when people ask, please tell a natural example. And then it was my plan to answer. Okay, but we will learn this later. So now I need to tell what is universal Turing machine. And so, well, I need to say a theorem. And so now we consider Turing machines that have two strings as input. And we understand we start them by writing the two strings separated by a blank. On the input tape, we start them and then we see whether they accept or reject. Okay, and so the theorem says that there exists a Turing machine that on input P and X. Well, okay, it can call how I want. No, that's X and P. Runs in time and shall we say length of X plus time P. Okay. Let's give it a name. And you. Okay. So here is our theorem. One table. Yeah.
Like propose constructing two tape machine and then merging it.
Yeah. I will follow your suggestions. So for the proof. So here is a theorem. So there is a single Turing machine. It receives a description X of another Turing machine and a program for this machine, or just an input for this machine, P. And it will run in time the length of the description.
Oh,
Yeah, sorry. Okay. So teacher is stupid, but fortunately students are clever, so we can get through. And so this runs in time order, length of X plus time of this simulating Turing machine for this program. So it's clear what I mean with this. Just the number of steps needed for this program to terminate, for MX to terminate on input P. Okay. And the simulation should return the same answer as MX. And so if one accepts, then he should accept. If it's reject, if it's undefined, if MX of P get in a loop or halts in another state, then the same thing should happen for UP. Okay, and so how will we prove it? Okay, so here I use descriptions of one tape Turing machine. I need to be a bit more precise. M of X. Where M of X is one tape.
it doesn't matter actually, because you can construct, like using the same idea, we construct if M is
Yeah, but I need to the power 4 then.
no, it doesn't matter. It doesn't matter even if M is a K-type machine, then we can start K plus 1 tape machine where like we have K tapes for memory and 1 tape for program.
Yeah, I agree if K is fixed, but if you take any multi-tape Turing machine, it doesn't work. Yeah,
Okay,
yeah. Okay.
no, we can simulate M. We can simulate. We can first simulate K.
Yeah. If you
For
make
any
the
K, we can simulate
yeah.
the K machine.
but we
one.
cannot make the proof too difficult. Otherwise, yeah, there is 1 minute left. It's perfect if we don't make the proof difficult. And so I will use simulate one tape machines. Okay, and so it's clear how it works. So the machine U will copy one part of the input to the other machine, to the other tape. So it will keep the description of the other tape on this machine. So here will be X, the instructions on what to do. So initially there is X here, there is a blank here, and there is a P here. So in the beginning, it will move X to this tape and put P in the beginning so that it's ready to simulate machine MX. So, and so on. Okay. And then each computation step will be the following. So its head will be above some cell here. It will scan the symbol. Then it will just look in the transition table of X, what needs to be written and which move needs to be made. Okay, but actually it's better even for the proof to have a third tape because it also, it needs to remember the state Q from the computation head. So let's write this on the third tape. And then it can look inside X, which symbol is written here, which Q is here, and it can copy this thing. So how much time is needed for this? So he needs to scan these things a constant number of times. So to simulate one computation step, the time will be order length of X. to scan these things.
So length of P,
No, so the program length can be arbitrarily long, but to simulate one step, it just needs to write one cell, read one cell, and write one cell. So it doesn't depend on the length of P.
yes, but which cell does it read? It needs to find the current transition.
Yeah, but this computation head stays locally above the cell that it's simulating. This doesn't go through all of the inputs.
Oh, P is input and X is the program.
Yeah,
Great convention.
yeah, sorry for this, I was stupid. Yeah. Okay, again, yeah, I don't know, I do okay, I will not change it, sorry for. Yeah, it's because I prepared a course on Kolmogorov complexity now, and all the inputs are programs. And I failed to switch my brain, so I agree. I need to be punished for this, but okay, you can. But don't worry, life. Okay.
The main question is how do we scan X and decide like how to change the state Q in polynomial time?
Yeah.
How do we decode X in polynomial?
Yeah. So here we have log gamma cells to encode one symbol of the simulated machine. So what he needs to do is just look at these cells and then go over the description until it sees the corresponding input for these cells. So he sees, okay, if you see this thing, then do this. So all the time it tries to find this sequence inside the description of the transition table.
How exactly we describe the machine?
Okay, there is a huge number of low-level details. I don't want to go over them.
Okay, but there is a way to describe all the machines. So
Yeah.
in the way so that we can do it in polynomial.
Yeah. So there is a bunch of low-level details. Just by the way, I will not ask this on the colloquium or the exam. I just want to explain that's not so difficult. Okay, so now we have three-tape Turing machine that solves U, and its runtime is order length of X times time of P, time mx on P. Okay, it's not so beautiful. And now we want to simulate this machine by a one-tape Turing machine. Okay, and it should not be plus here, but times here. And so we have M. So one step costs us something proportional to the length of X. The number of steps we need to do is, so this needs to be multiplied by time of MP of X. Mx of P. So this will be our runtime. Okay, and so here we have universal Turing machine. And that means that we have proven P is not equal to X. So there is a more precise version. It's time hierarchy theorem. And this, I will just say it, I will not prove it.
Can you write the theorem's name, please?
Yeah, so just hierarchy theorem, it's called. It's written in the title of the lecture on the wiki. So time hierarchy theorem says that if F is time constructible, so it just some simple property, like all polynomials have this property. Yeah, it means that on input a string of 0 ends, so on input n in unary, it produces f of n in time order f of n. Okay, I write the definition, so just 5 minutes. Oh, we are already over time.
Minus 5.
Yeah, okay, yeah. if f is time constructible, then and g is smaller than f of n, g of n is small o of f of n divided by log f of n. So if g is just a little bit smaller than f of n, then time f of n not equal to time g of n. Okay, and actually I should not write the arguments because we are serious people. I mean, if normally if they're like intellectual computer science, there are quite some mathematicians, they hate if you write the argument and okay. So this is the theorem, and something similar for space is also true, but here we don't need this logarithmic factor. Okay.
No.
Yeah, the space hierarchy theorem, this is time hierarchy theorem.
Is it known that can we remove that logarithm or replace with the?
No,
double
it's
logarithm?
open question. And it was probably very difficult to open. I mean, for one-tape Turing machines, there exists some result, but I forgot the details. But you told me, no, somebody else. Yeah, something happened for one-tape Turing machines. But the normal definition is time with multi-tape Turing machines. But okay, now we do what Zipfer does to keep things simple. Okay, so let's finish, but then the seminar should start 10 minutes later, right? At 7:50 instead of 7:40. Okay, see you next week. Thank you. Yeah, I promise I will explain better, but it was already better than previous years.